When I released CANT back in January, there was one thing that CANT couldn't do at the time, and I figure if I'm going to release a tool called CANT, I should probably make sure there's nothing that CANT can't do. The thing that CANT couldn't do at the time was CANT couldn't assert a recessive state on the bus. This is how CAN handles all of its arbitration, all of its error handling and error recovery, is by assuming that a node cannot assert a recessive state on the bus, that if any node on the bus is asserting a dominant state, then the state of the bus will be in the dominant state. So in order to accomplish this, I created this piece of hardware. It's a shield that plugs into the Nucleo STM32H7ZI dev board that we've been using. And it is a standard CAN transceiver. It has a, you can focus. There we go. It has a CAN transceiver, connector, a couple passives on it. The thing that I added that makes this special is this little device here at U2. It's an analog switch, and what this analog switch allows me to do is it allows me to short CAN high and CAN low together. And when CAN high and CAN low are shorted together, it will cause any node on the bus to read a recessive state because they'll be at the same potential. So this allows me to violate that last inviolable for the CAN bus, is by asserting a recessive state on the bus. And this allows me to create two new attacks, plus adding a enhancement to a third attack. So the first attack I'm going to demonstrate is the cyber paperclip mode. This just turns on the bus. It does the same thing that shoving a paperclip into the CAN bus would do. It just causes the buses to short together and nobody can communicate. We'll go ahead and start that attack, the bus short attack. And we see that this purple line here on the scope is the state of the switch. So we see that this went high, turned the switch on, and that now we don't really have any traffic on the CAN bus. At some point we should be able to see some sort of message start to come up. We can see that the instrument cluster is dead. We see it's kind of trying to send a message here and there, but it's not able to actually send anything because the bus is shorted together. Go ahead and reset our CANT. Reset the car because recovering from this is difficult. I'll go ahead and get the instrument cluster running again. The second attack I want to demonstrate is a NAC attack. So what the NAC attack does is it tries to essentially clobber the acknowledgement bit that the nodes on the bus are supposed to send back once they properly receive a message. So go ahead and set our baud rate. Choose the NAC attack. And this should, as we see here, this is where the NAC slot should be here on the scope. We see that our switch goes high for one CAN frame or one CAN bit, and it does all this, cause all this crazy stuff to happen on the bus, all this noise to happen. So as we can see, our instrument cluster is still running. It seems like it's still getting enough back that it's not, the car isn't too unhappy. But we're able to generate a bunch of noise on the NAC frame. The last attack I want to show is an improvement to the data replacer attack. Well, previously, the data replacer attack would only work if we were wanting to send a dominant bit where a recessive bit was being sent. The brake fluid test that I showed in the previous video showed that. The brake fluid level low is a dominant state, so I was able to assert that dominant state on the bus and have the brake fluid level low show up on the bus. But what if you want to go the other way? So in this case, I've actually used our control box to cause the body control module to actually be sending the brake fluid level low, which is it does by setting that bit to 0 to the dominant state. And now I want to overwrite that with the recessive state for that bit to cause the brake fluid level low light to turn off. I was unable to do that with the previous version of CANT, but now I can do that. So we go ahead and set the arbitration ID, choose the baud rate again, and do the data replacer attack. Set 8 bytes. First byte will be 98, 00, 01, 06, 00, 00, 00, 00. Then I added this line here, the forced recessive bit. Forced and recessive is not currently the default. I'm going to go ahead and say yes to force the recessive bit, and we'll see here that the brake fluid low light goes away. Now we will see occasionally that the brake fluid low light will flash back on for just a second and turn back off. I haven't been able to figure out why that is happening. If we go and look at the actual state of the bus using the CANT tool that I have hooked up, we can see that it's all of the brake fluid message lights are being set to what I set it to. It's sending 98s all the way across. There's some other behavior in the instrument cluster that's causing that message to pop back up occasionally. But the attack works. All of the messages that we're targeting are now coming across the bus with the correct value.